Section 3.11, related rates. A rate in this section is a derivative with respect to the time. For example, the velocity of a moving object is the derivative of the position of the object with respect to the time. The velocity of a moving object is the rate of the change of the position of the object. The title of this section is related rates. That is, in this section, we need to relate a rate to some given rate. When you solve a problem in this section, I suggest the following 4 steps should be used. Step 1, draw a diagram about the problem. Step 2, introduce variables. Step 3, determine what are given to us and what we need to find. Step 4, relate the unknown rate to the given rates. Now, I illustrate these 4 steps with some examples. Example 1. A rectangle initially has dimensions 2 cm by 4 cm. Initially here means the time is 0. All the 4 sides of the rectangle begin increasing in length at a rate of 1 cm per second. Now the question is, at what rate is the area of the rectangle increasing after 20 seconds and after 40 seconds? To answer the questions in the example, step 1, draw a diagram. I draw a rectangle. Step 2, introduce variables. I let x denote the length, y the width, and a the area of the rectangle. Please note that all the 4 sides of the rectangle are increasing in length. Therefore, this rectangle is not fixed. The size of the rectangle is increasing. As a result, x, the length, y, the width, a, the area of the rectangle, all are changing. X, y, and a, they depend on the time t. Therefore, they are functions of time t. Step 3, determine what are given and what we need to find. Initially, the dimensions of the rectangle are 2 by 4. In other words, when time is 0, x is 4 and y is 2. All sides begin increasing in length at a rate of 1 cm per second. A rate in this section is a derivative with respect to time t. The increasing rate of the length of the rectangle is 1. In other words, derivative of x with respect to the time t is 1. The increasing rate of the width of the rectangle is 1. That is, derivative of y with respect to the time t is 1. These are all given to us. At what rate is the area of the rectangle increasing after 20 seconds? To answer the question, we need to compute the derivative of the area with respect to the time t. The derivative is the increasing rate of the area at a general time t. After we get the derivative, plug in 20 in the derivative. Then we have derivative at 20. Derivative at 20 is the increasing rate of the area after 20 seconds. Similarly, at what rate is the area of the rectangle increasing after 40 seconds? To answer this question, we need to compute the derivative of the area with respect to time t. Then evaluate the derivative at 40. Step 4. Relate the unknown to the givens. The unknown is derivative of the area. The givens are derivative of x and derivative of y. One relation between area, the length, and the width is a is equal to x times y. Now, take derivative with respect to the time t on the both sides of this equation. Then I have this equation. About this derivative, the function is a product. Please note that x, the length of the rectangle, depends on the time t. So x is a function of the time t. Y, the width of the rectangle, depends on the time t. Y is a function of time t. Now, take derivative on x times y with respect to the time t by the product formula. The derivative is derivative on the first function x times the second function y plus x times derivative of y. This is the derivative of the area at a general time t. This is the increasing rate of the area at a general time t. Now, consider the time instant when t is 20. When the time is 20, the length is 4 plus 1 times 20. Initially, the length is 4. And the increasing rate of the length is 1 cm per second. So after 20 seconds, the length is 24 cm. Similarly, the width is 2 plus 1 times 20. Initially, the width is 2. The increasing rate of the width is 1 cm per second. After 20 seconds, the width is 22 seconds. At the time when time is 20, the increasing rate of the length is 1 constant. The increasing rate of the width is 1 constant. Now, plug in all this information in this equation. The rate of the area at time is 20 is plug in 20 in the time in this expression. When time is 20, dx dt is 1, y is 22, x is 24, dy dt is 1. So the sum is 46. and the units is cm squared per second. Conclusion: the rate after 20 seconds at which the area is increasing is 46 cm squared per second. The second question: at what rate is the area of the rectangle increasing after 40 seconds? When time is 40, the length of the rectangle is 4 initial length plus 1 the increasing speed or increasing rate of the length times 40 seconds is 44 cm. When time is 40, the width is 2 initial width plus 1 increasing speed of the width times 40 is 42 cm. When time is 40, increasing rate of the length is 1, a constant. Increasing rate of the width is 1, constant. Plug in all this information into this equation. Then increasing rate of the area at the time 40 is this. When time is 40, dx dt is 1. Y is 42. X is 44. dy dt is 1. This sum is 86. The unit is cm squared per second. Now, conclusion. The rate after 40 seconds at which the area is increasing is 86 cm squared per second. Example 2. Car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Look at this diagram. Car A is traveling west, and car B is traveling north. Both are headed for the intersection of two roads. Now the question is, at what rate are the two cars approaching each other at the instant when car A is 0.3 miles and car B is 0.4 miles from the intersection? To answer the question, step 1, draw a diagram. I'm done with this step. Step 2, introduce variables. I let C denote the intersection of the roads. And the distance between car A and point C is denoted by X. The distance between car B and point C by Y. The distance between the two cars by C. Please note that X, Y, and C, they are changing. They depend on the time t. So they are functions of the time t. Initially, when time is 0, car A and car B may be very far from the point C. Because A and B are traveling toward the point C, there must be some instant when car A is 0.3 and car B is 0.4 miles from the intersection point C. Let me denote the instant by t0. So when time is t0, x is 0.3 miles and y is 0.4 miles. Step 3. Determine what are given and what to find. When time is t0, x is 0.3, y is 0.4. Car A is traveling at the speed of 15 miles per hour. This is the rate of change of the distance x. So derivative of x with respect to the time t is negative 50. By negative, I mean x, the distance between A and C, is decreasing. Car B is traveling at the speed of 60 miles per hour. 60 miles per hour is the rate of change of the variable y. So derivative of y with respect to the time t is negative 60. The negative means y is decreasing. What we need to find? We need to find the rate at which car A and car B are approaching each other at the instant when car A is 0.3 miles and car B is 0.4 miles from the intersection point C. That is, we need to find the derivative of C with respect to the time t. C is the distance between the two cars. Derivative of C with respect to the time t is the rate of the change of the variable C. It is the rate at a general time t. After we get the derivative, plug in t0 in the derivative to get the rate at the instant t0. Step 4. Relate the unknown to the givens. The unknown is dc dt. The givens are dx dt and dy dt. We need to find a relation among them. A relation among x, y, and z is given by the pi diagram theorem. By pi diagram theorem, c squared is equal to x squared plus y squared. That is this equation. Now, take derivative with respect to the time t on this equation. Then I have this equation. Apply the summation rule to this derivative. Then I have this equation. Apply the chain rule to each of these three derivatives. Then I have this equation. For example, by the chain rule, I can write this derivative as the product of these two derivatives. If I cancel dc, then the product returns to this derivative. Derivative of c squared with respect to c is 2c. Derivative of x squared with respect to x is 2x. and derivative of y squared with respect to y is 2y. Now, divide this equation, the both sides, by 2. Then I have this equation. Don't forget, I'm looking for dc dt. I move c to the right side. Then I have this equation. This is the derivative of c with respect to the time t. Now, consider the instant t0. At t0, x is 0.3, y is 0.4. C by pi diagram theorem is 0.5. And derivative of x with respect to the time t is negative 50. Derivative of x with respect to the time t is the traveling velocity of car A. Car A is traveling at a constant velocity. Derivative of y with respect to the time t is negative 60. This derivative is the traveling velocity of car B. Car B is also traveling at a constant velocity. Plug in all this information in the derivative of c with respect to the time t. Then we get derivative of c at the instant t0 is this. At time is t0, c is 0.5. X is 0.3. dx dt negative 50. Y is 0.4. dy dt negative 60. Here there is a typo. By calculator, this number is negative 78. The unit is miles per hour. Negative means the variable c is decreasing. Now, conclusion. The two cars are approaching each other at a rate of 70 miles per hour at the instant t0 of time. t0 is the instant when car A is 0.3 miles and car B is 0.4 miles from the intersection of the roads. Example 3. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall at the instant when the bottom of the ladder is 6 feet from the wall? To answer the question, step 1, draw a diagram. This is the diagram. This line represents the ladder. The length of this line is 10 feet. Step 2, introduce variables. Between the wall and the bottom of the ladder, the distance is denoted by x. And between the top of the ladder and the ground, the distance is denoted by y. Because the bottom of the ladder is sliding away from the wall, these two distances are changing. X and y depend on the time t. So x and y are functions of the time t. Initially, when the time is 0, the bottom of the ladder may be somewhere close to the wall. As the bottom sliding away from the wall, there must be an instant when the bottom is 6 feet away from the wall. I denote that instant by t0. That is when time is t0, x is 6. Step 3. Determine what are given and what to find. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. 1 foot per second is the rate of the change of this distance. This distance is denoted by x. So 1 foot per second is the rate of the change of x. On the other hand, the rate of change of x is derivative of x with respect to the time t. So this derivative of x with respect to the time t is equal to 1. Moreover, when time is t0, x is equal to 6. And the length of the ladder is 10 feet. These are all the information that we have. About what to find, we need to determine the rate at which the top of the ladder sliding down the wall at the instant t0 when the bottom of the ladder is 6 feet from the wall. That is, we need to compute the derivative of y with respect to the time t. This derivative is the rate of the change of the y variable. Y variable is the distance between the top and the ground. After we compute this derivative, evaluate this derivative at the time t0. Then this is the answer to this question. Step 4. Relate the unknown to the givens. The unknown is dy dt, and the given is dx dt. To find a relation between these quantities, I start with the pi diagram theorem. Consider this right triangle. By the pi diagram theorem, tan square is equal to x square plus y square. So I have this equation. Take derivative on the both sides with respect to the time t. Then I have this equation. Derivative of a constant is 0. Apply the summation rule to the derivative on the left, then I have this equation. Now, apply the chain rule to each of these two derivatives. Then I have this equation. Derivative of x squared with respect to x is 2x. Derivative of y squared with respect to y is 2y. Divide this equation by 2. Then I have this equation. I'm looking for dy dt, so I solve this equation for dy dt. I move the first term to the right side, then I have this equation. And move y to the right side, then I have this equation. This is the derivative of y with respect to x. Now, consider the instant t0. At t0, x is 6. From this equation, y is 8. Derivative of x is 1. Plug in all this information in this equation. Then the rate of y at the time t0 is this. At t0, x is 6, y is 8, dx dt is 1. So simplify a little bit, we get the rate at t0 is negative 3/4. And the unit is feet per second. Conclusion. The top of the ladder is sliding down the wall at a rate of negative 3/4 feet per second, when the bottom of the ladder is 6 feet from the wall. The negative means the y variable, or the distance between the top of the ladder and the ground, is decreasing. Example 4. A 5-foot tall woman walks at 8 feet per second toward a straight line that is 20 feet above the ground. Part 1. What is the rate of change of the length of her shadow when she is 15 feet from the straight line? Part 2. At what rate is the tip of her shadow moving? Solution to part 1. To answer the question in part 1, step 1, draw a diagram. Here is a diagram. This is the 5-foot tall woman, and this is the straight line pole. The pole is 20 foot tall. Step 2, introduce variables. The length of the shadow, I denote it by x. And the distance between the woman and the light pole, I denote it by y. Because the woman is walking toward the light pole, x and y are changing. They depend on the time t. So they are functions of the time t. Step 3. Determine what are given and what to find. The woman is walking toward the light pole at the speed of 8 feet per second. So the distance between the woman and the pole is decreasing at the rate of 8 feet per second. The distance is denoted by y. Therefore, the rate of change of y is 8 feet per second. In other words, derivative of y with respect to the time t is 8. I add a minus sign because y is decreasing. Moreover, the woman is walking toward the light pole. There must be some instant when the woman is 15 feet from the straight line. I denote that instant by T0. When time is T0, y, the distance between the woman and the light pole, is 15. These are the information that we have. About what to find? We need to find the rate of change of the length of her shadow at the instant T0 when she is 15 feet from the street light. That is, we need to compute the derivative of x with respect to the time t. X is the length of the shadow. After we compute the derivative, evaluate the derivative at the time T0. Step 4. Relate the unknown to the givens. The unknown is dx dt. The given is dy dt. I want to find a relation between these two quantities. A relation between x and y can be obtained by similar triangles. Look at this diagram. The triangle ABC is similar to the triangle ADE. Because these two triangles are similar, the ratio of their corresponding edges is constant. Therefore, AD, this edge, over AB, this edge, is equal to DE over BC. AB is x plus y. X plus y, this is an AD. Over x is AB. AB is x. Is equal to DE. DE 20. Over BC. BC is 5. So I have this equation. Now simplify the equation. Move x to the right side, 5 to the left side. Then I have this equation. Continue to simplify the equation. Distribute 5 to x and to y. Then I have this equation. Cancel 5x from the both sides. I have this equation. Move 15 to the left side. I have this equation. Now, take derivative on the both sides of this equation. Then I have this equation. Now, evaluate the derivatives at the time T0. dy dt is negative a. Negative a is the walking velocity of the woman. The woman is walking at a constant velocity. Plug in negative a in dy dt, then we have negative 8 over 3. So the decreasing rate of the length of the shadow at the time T0 is negative 8 over 3. Conclusion: the rate of change of the length of her shadow is negative 8 over 3 feet per second at the instant when she is 15 feet from the street line. Negative means x is decreasing. Part 2. At what rate is the tip of her shadow moving when she is 15 feet from the street light? To answer this question, again, we need to draw a diagram. Here I draw the same diagram as in part 1. Step 2. Introduce variables. I still use y to denote the distance between the woman and the light pole. But this time, I use x to denote the distance between the tip of the shadow and the light pole. Step 3. Determine what are given and what we need to find. Just like in part 1, derivative of y is negative a. This is the walking velocity of the woman. When time is t0, y is 15. We need to determine derivative of x with respect to the time t and evaluate the derivative at the time t0. Step 4. Relate the unknown to the givens. One relation between x and y is from similar triangles. The triangle ABC is similar to the triangle ADE. Therefore, the edge AD over the edge AB is equal to the edge DE over the edge BC. AD now is x. AB is x minus y. Therefore, I have this equation. Simplify this equation. Move x minus y to the right side and move 5 to the left side. Then I have this equation. Distribute 20 to x and to y. I have this equation. Cancel 5x from the both sides. I have this equation. Divide the equation by 15. Then I have this equation. Now, take derivative on the both sides. Then I have this equation. Evaluate both sides at the time t0. dy dt is negative a, doesn't depend on the time. Plug in negative a in dy dt here, then I have this equation. This number is negative 10.67. Now, conclusion. The tip of her shadow is moving at the rate of negative 10.67 feet per second when she is 15 feet from the street light. Negative means the distance between the tip and the light pole is decreasing. X is decreasing, so negative.